All right, now it's time to introduce another friend. Boy, this thing is long and complicated, and it looks like it. It is, you know, but it's not so much. All right, this is called Bernoulli's law, and if we look at it, it has a few terms in it. At the start, we have P1, 1 half, and instead of saying mv squared for kinetic energy, we have 1 half rho v squared. And then here we have, instead of mgh, we have rho gy. So if we look here, this is actually based on the law of conservation of energy, start equals n. Now let's look at the end. At the end we have some pressure, we'll call it P2. 1 half, and instead of mv squared again, we have rho v squared. This is 2 because it's at the end. And instead of mgh, we got rho gy. Same thing. So when we look at this, conservation of energy, it's very, very similar to start equals n, and it really indeed is based on that. Now, if you want to see a proof of that, all right, we actually have that available to you. So if you look, it's somewhat long and complicated. So if you want to put that on pause and take a look, you can actually see the proof right here based upon start equals n, and voila, there it is. All right, now, as we look through this, the question is, what do we do with this Bernoulli's law? Well, Bernoulli's has to deal with a couple things. It's all about pressures, velocities, how fast the things are moving, and heights, how high things are. So, for example, in buildings, there are pipes within a building. All right, pipes have water flowing through them at a certain velocity. I think it's important to us to have the water come out pretty fast. So if you take a shower or a bath or wash your hands, you don't want the water just dribbling out. Maybe you've been to somebody's house and the water pressure is really bad. You go, oh man, I hate this shower. You know, you can't get water pressure and you can't actually get yourself clean because of it. People actually go through and actually design these things using Bernoulli's law so you can actually figure out how fast the water is going to come out when you set the pipes up. All right, so this equation helps us when we're dealing with things that flow through things like pipes. All right, now, I just happen to draw a couple pipes over here. And we have a big pipe here, and then it goes into a narrower pipe like so. Now, for simplicity reasons, I'm going to call the center of this pipe 0. And at the other end, it also has 0 height. So this is not a situation where the pipes are going up into the top of a skyscraper. It's not a situation where things are changing elevation. The center of the pipe stays exactly the same no matter what. All right, now, as we go through, there's a velocity, and the water is actually moving through these pipes, and there's a certain pressure. So at this point in time, let's say the pressure here, P1, is, let's make it fairly realistic, 100,500 pascals. Okay, so that's the pressure of the water in that side of the pipe. Now my question is this: what is the pressure on this side, on the end side of things, here in the smaller side of the pipe? Now there's a couple things I did note. The velocity of the water in this side of the pipe is 10 meters per second. And the velocity of the water in this side of the pipe is slightly more than that. Well, you know what? Can I actually calculate what the velocity of the water is in both sides of the pipe? If we go back to the previous lesson, we know that the area, A1, that would be the area of this pipe, cross-sectional area. If you need that, you just go, ah-cha! Chop the pipe in half, and it's how big that circle is. And on this side, we have the area of this piece, which we call A2. And we know that the velocity is proportional to that size of the area. So we know that area 1 times the velocity here is equal to the area of this one times the velocity there. All right, now let's suppose, I'll just make up something. If we have certain areas on this side, let's suppose it results in a velocity here on this side of the pipe of, let's say 12 meters per second. I just made that up. So if we knew the areas, we could actually calculate it exactly what that velocity would be. All right, now let's see how this impacts Bernoulli's law. So we look, our original pressure is 100,500 pascals. Plus, all right, now on this side, our velocity is 10 meters per second in the bigger side of the pipe. So we're going to end up with rho, which is 1,000, times the velocity, which is 10. plus. All right, now, when we look here, what is the actual height of the water in this pipe? Well, we're right in the middle of the pipe is 0, so there's water above, water below. So on average, there is no height to that water, so we cross that off. All right, so we end up, that equals. All right, pressure on this side is our unknown. We don't know what that is. That's what I'd really like to find out. Plus 1/2 rho, which is 1,000, times the velocity on this side, probably calculated using our areas, of 12 meters per second. Don't forget to square that. Oops, forgot to square over here too. All right, and the height. When we look here, isn't the center of that pipe at 0 on the small side as well? Half above 0, half below. So it averages out, and we don't have any height change. So we look here, we can go back, and then let's plug in the numbers and recalculate what the pressure is in that side of the pipe. So as we go through that process, according to my calculations, the pressure on this side is going to drop to 78,500 pascals. So a very interesting effect. Now, notice as the velocity goes up, what happens to the pressure? Ooh, interesting. So when the velocity increases, the pressure actually goes down. So in this case here, velocity is 12, this one's 10, pressure goes down. Velocity here is lower, pressure goes up. They're opposites of each other. Now we see this effect in that particular situation where when velocity increases, the pressure declines. So for example, in a hurricane, the wind is blowing very, very fast, so the wind goes by and sucks the roof off the house. Or you see in a tornado, you know, like a movie like Twister or something like that, and then all of a sudden you see a cow fly by, it got sucked out of the barn or something like that. That's because of the actual movement of the air itself. So I was thinking about this today. I was drinking chocolate milk for lunch, so I had to get the chocolate milk out of the carton, but I didn't want to put my mouth on the carton because the outside was dirty. So an interesting invention. I picked up a straw. There was a whole bunch of them in the cafeteria, and I observed other people doing this. So what they do is, to try to get the chocolate milk from the carton into your mouth, you make a motion like shh, and you suck air out of the straw, lowering the pressure because you've increased the velocity of the air by going shh. Pressure drops inside your mouth. Air pressure pushes the milk up through the straw into the low pressure area inside your mouth. You might say, oh, I sucked the milk out of the straw and blah, 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 blah. Not true. You increase the velocity of the air in your mouth, which lowered the pressure, and then the atmospheric pressure outside the straw pushed the milk right up the straw into your mouth. So that's a great example of increasing velocities lowers pressure. All right, so Bernoulli's has a lot of effects on that. Now, this is a fairly simple example here. So this it's just a matter of simply putting a few numbers in there and then recalculating that.